I'm starting to record now. And so I forgot to get I've got the iPad connected, but I forgot to start, um, start notes. And right, that's the right one. Okay, so we got a new note. Okay, let me get rid of this photos thing. That's all right. So, let's see. Just wondering, do any of you want to ask questions verbally as opposed to using the chat session? If so, I can just list the recording privately and send you guys the link instead of listing it publicly. Well, let me start by saying that that this business here of integral equations can be confusing. And the reason it can be confusing is that, for example, in this particular case, we've got u of x and p of x and u prime of x and so forth. But then we convert it to an integral equation, and we have now p of y and r. Oh, that should not be r of z. That's a mistake. That should be r of y. Oh boy, it occurs again. Sorry about that. Let me just fix it on the fly. And then it involves this unfamiliar Cauchy identity, which, as I said, is a special case of the even less familiar and more sophisticated Cauchy identity. Monsieur Cauchy was a very talented man. And so what we wind up with is a rather complicated integral formula in general. It's u of x is u of a plus x minus a u prime of a plus x minus a p of a u of a plus integral a to x, and then this kind of complicated integral. So of course, I could have factored that and made it a little more simple. So I won't do that now, but you can see that u of y multiplies p prime, p, and q. So obviously you want to take that out. On the other hand, it doesn't multiply r. So I thought what I'd do is give you an example of starting from a differential equation and going to the integral equation. And so the one that I worked out this afternoon as an example, and let me first get rid of this business here. I don't know what I was intending to write when the pen ran out of electrons. So let me switch to black and just draw 2 lines. So this is 26 October. So the idea was or my thought was to take you through this particular example. U double prime is equal to x squared u prime plus xu plus sine of x. And so what do we have? Well, we have p of x is x squared. Q of x is x. Somebody has a pet that's growling, which I guess is okay. Anyway, r of x is sine of x. Now, again, I just worked this example out this afternoon. I could have made a mistake. So what do we have? Well, the kernel, k of x and y, what is that by definition? Let me see if I can make this just a little narrower. What that is by definition is the kernel is oh, you're not seeing this. Hold on. This is a big mistake here. Sorry, I started it and I just forgot to make it so that you could see it. QuickTime Pair, new movie recording, iPad 3, boom. Okay, so that's what I was writing down. And so what we do is we apply this. It's equal to P of y plus x minus y times Q of y minus P prime of y. So as I said, this can be confusing. And so let's just see what it is in this particular case. Well, P of y is y squared. And then we have, I'm so tired of this thing switching to the, so we have then x minus y times q of y. Well, q of y, q of x is x, so q of y is y. And now we have minus p prime of y. Well, p prime is 2x. So p prime of y is 2y. And then we subtract 2y. Okay. So what we see here is that this is equal to y squared plus x minus y times minus y. And that gives us 2y squared minus xy. And I think that in my solution, I made a mistake. What did I say? Oh, no, I got it right. Okay. So k of xy is 2y squared minus xy. And now, to finish the problem, in other words, the first thing with an integral equation is you've got to figure out what the kernel is. So we've just done that. The next thing is you have to figure out what f is. And f is sort of straightforward. It's this thing in the beginning here. And what I decided in the example was I chose the interval 0 to 1. And that's very convenient. Oh, before I go on, let me just mention something about these solutions. So this is the general solution. K is that, and F is this. Notice that the integral equation builds in the boundary conditions. One boundary, the interval is a to x, and the lower limit then occurs in the integral, but it also occurs in the definition of the function f. In other words, f of x is u of a plus x minus a, u prime at a minus p of a u of a, and so forth, and then another integral starting at a. So the boundary conditions, in other words, what a is comes in an important, it comes in multiple places, and it's just is an it comes in more forcefully than for a differential equation. With differential equation, we say, all right, here's the equation. We got to figure out what the function is, and then to make it unique, we have to we need two boundary conditions, but we sort of leave those boundary conditions off to one side until we've solved the equation. Whereas here, with an integral equation, the boundary conditions show up right away in the function f. They don't show up in the kernel, but they show up in the integral and in the function f of x, and in many places in that definition of the function f of x. So in this particular case, what is f of x? Well, f of x is equal to u of 0, because I took a to be 0. And taking a to be 0, this thing simplifies. It's just x. And then we have u prime at 0. And then we subtract p of 0, but p is x squared, so p of 0 is 0. So I don't need anything more. And let me try to fix this. This is u prime of 0. And then we have an integral. And the integral is integrals from 0 to x. And now we have to put k in there. So k is 2y squared minus xy. I'm trying to find x simply. So it's these things that we've already done. And then an integral a to x of, well, you see, I've made a mistake. That's what I said. This is actually fairly confusing. And that doesn't mean you shouldn't learn it. It just means that you have to keep both eyes open and stay awake while you learn it. So f of x is these terms that I've written down, and then it's an integral x minus y times r of y. And r in this particular case is is the sine function, so this is sine of y dy. Now, this last integral you can do. I frankly used Mathematica to do it. I could probably have used MATLAB, but I just chickened out and used Mathematica. And what I got here was the integral was x minus sine of x. So altogether, Jesus Christ. Does anybody know how to prevent this thing from automatically switching? Anyway, f of x then is u of 0 plus x u prime of 0, and then plus this integral, and the integral is x minus the sine of x. So that's f of x. And then what is the analysis that we went through yesterday? What did it tell us? Well, it said that u of x is then f of x plus, an integral from a to x of k of xy. Well, k of xy is 2y squared minus xy. And now we multiply that by u of y dy. Now we can't do this integral because it involves the unknown function u. We know what f is, but we don't know what u is. So this is our equation. And in full detail, it is u of 0 plus x u prime of 0 plus x minus sine of x. That's a little obscure, isn't it? All right, let me try to fix this. Sine of x plus then this integral from, oh, and a is 0. So over here, what we actually have is 0. And so here we have integral 0 to x of 2y squared minus xy u of y dy. And as I said, we can't do this. We just have as our equation u of x equals this. You notice the boundary conditions are built in. You have to put in a number for u of 0 and a number for u prime of 0. And anyway, so there is a nice integral equation, the integral equation for this particular differential equation that I just, invented. I just wanted a simple case, and I took the lower limit to be x equals 0 to make things simpler, to eliminate having to go through unnecessary trivia. All right, so that's an example then. And I think yesterday I went through these two examples. So maybe I'll go on to the next chapter and look at some examples there. So let me move this out of the way if I can. And so, as I said, the Legendre polynomials are, they have funny sort of conditions. One is a normalization condition. The nth, every Legendre polynomial at x equal to 1 is equal to 1. And then secondly, the Legendre polynomials are orthogonal when, in other words, Pn and Pm are orthogonal if n is not equal to m. And maybe we can just go through how you construct them. P of 0 turns out to be just 1. What we know is that. So let me start over with a different color, maybe green. So so we have the conditions Pn of 1 is equal to 1, and integral minus 1 to 1 dx of Pn of x, Pm of x is 0 if n not equal to m. So these are the two conditions here. Let me try to write that a little bit better. So in as much as P0 is a constant, and it has to equal 1 when x is equal to 1, then it's just the constant 1. Something that's orthogonal to the number 1 is the function f of x, p1 of x equal x, because then what you have is, if this is the interval -1, 1, then p0 just looks like this. And then P1 does this. And obviously it's orthogonal to P0 because P0 is a constant. And here what you've got is you have just as much negative as positive, so they cancel. To make P2, you know that P2 of well, let's just say it. P2 of x is going to be, how did I say it? A0 plus A1x plus A2x squared, say. Now, we want to set A1 equal to 0 because this is just P1 itself here. So we're going to set this term, we're going to set this term equal to 0. And then we have the normalization condition that 1 is equal to A0 plus A2. And what else? Well, we know that the integral -1, no, that's not going to give us anything. Well, let's see, the orthogonality condition here. That's right. P2 has to be orthogonal to P0. And so it has to be something that integrates to 0. So in other words, P2 of x -1 to 1 dx has to be 0. And so that is 2 times A0 plus A2, the integral of x squared, and that would be 2 over 3. And so that's this condition here. And so that gives us that P2 is 3x squared minus 1 over 2. So in other words, this says that A2 is equal to minus 3 times A0. And one can then take A0 equal to, well, another way of looking at the normalization conditions that we saw yesterday was A0 plus A1 plus A2 is equal to 1. So in any event, one then finds that P2 is 3x squared minus 1 over 2. And then you can find the others that way. Rodriguez has a very nice formula involving derivatives. As I said, there's a generating function. We saw this last time. And then one then can find that what the differential equation is, which is Legendre's equation in self-adjoint form. We already found that. I think I showed you yesterday the Legendre series for the Dirac delta function. It's, of course, a sum on all n from 0 to infinity of Pn of x prime. And then you multiply by, and I forget what these are actually. I think this is Pn of 0 and Pn of 1. But let me, it's a normalization factor in this particular case. So let me, since I've actually forgotten what the trick was, if we go back to does anybody have, well, I could look in the index and that would do it, but yeah, it's might be under completeness. Ah, there it is. So what you have is the weight function at two different points, and so in order to find the weight function, you need to know what Legendre's equation is in self-adjoint form. And so if we go back to here, there's the differential there's rho here, and let me, here I've got nn plus 1. So it's simply, all right, I must say I'm a little confused about this. I don't quite, oh, that's, I don't see rho here. All right, well, I'm going to have to think about this. It's, this normalizes the Legendre polynomials, but I don't see rho here. In fact, it may be that I was careless and just normalized them instead of finding the weight function. In this case, we've seen that the weight function is just a constant because the Legendre's equation is, I mean, here's rho of x, it's a constant. The question is, what is the magnitude of that constant? And one could just take it equal to 1. If we took it equal to 1, then I just have a 1 here. And that would give a different number, wouldn't it? It was back here when we were talking about completeness of the eigenfunctions. These eigenfunctions were normalized, and they were normalized with respect to a weight function. If the weight function is unity, then they just have to be simply normalized. I think I should actually explain this in the book a little more carefully. So what we sort of come upon here is that you have to normalize the weight function. You normalize the eigenfunctions with respect to a weight function, and so in other words, the general form is this. So let me write it down for you. It would be delta of, in fact, let me try to make this a little bit amusing. X minus what? Shit. Y is, and so it's, let's just say rho of x, just to make it simpler. And then it's a sum on all I, and of course I could start at 1 or it can start at 0 depending on how you number the eigenfunctions. And then it's ui of x, ui of y. Here I'm thinking of them both being let me actually just get rid of it. All right, so y. And now what is true of these the u's, and it's that delta ij is equal to an integral rho of x ui of x uj of x dx. So they're orthonormal with respect to this weight function on whatever the interval is, and I'll just call the interval AB. So that's the way we actually that's the general form of the delta function. You have a rho, and then these u's are already normalized. They're orthonormal with respect to the weight function. Here I didn't bother to state that precisely because we had already sort of gone through that, and we knew that when we were studying these things, but at this point I forgot. And so if we go now to the to Legendre's differential equation, where is it? Well, first of all, we here's the normalization condition for Legendre polynomials, namely it's 2 over 2n plus 1 is equal to times delta n m is equal to an integral minus 1 to 1, and it's Pn of x Pm of x dx. And if we look at the differential equation, here's the differential equation. The differential equation is minus 1 minus x squared p prime n prime is equal to n plus 1 Pn of x. Well, this tells us that rho of x is equal to 1, and this tells us that also. So in both of these, here, let me. In both of these equations, in this equation and in this equation, we see rho of x is equal to 1. But in order to normalize the thing, what we have is delta nm is then equal to minus 1 Pn of x Pm of x dx, and we have to divide this guy by square root of 2 over 2n plus 1, and this guy by 2 over 2m plus 1 plus 1. Okay, so that's the way that thing looks, and consequently, we have rho is equal to 1, but we need the normalized Legendre functions, and so the delta function, delta of x minus y, is then a sum. It has a 1 because that's the and so this would be Pn of x, Pn of y, and now we have to normalize them, and so we divide by this times that, or divide by this squared, and that gives us 2n plus 1 over 2. which is what I said here. So that's the full derivation of this, and I think it was good to go through that. Anyway, we see that that's actually what does give the correct answer here. Of course, we could have multiplied the wave function, no, actually we couldn't. The graph would look more or less the same if we had an overall positive constant on the right-hand side. If we multiplied Pn, and if we got the normalization wrong by a positive number, the graph would look okay, but it still wouldn't be a delta function because the normalization would be off. So there are various recurrence relations for the Legendre polynomials, and what you've got then is a fairly cute way of computing the Legendre polynomials. In other words, you know what we just worked out what the first three polynomials were, but really you only need the first two, P0 and P1. And so this would give P2. In fact, let's just look at that as an example. What we'd have would be P2 of X would be 1 over 3, and it would be 2n plus 1. So n is 1 here. So this is then 3. X, P1, that's X. So that's X squared minus n is 1, P0. P0 is 1. And you remember that's, well, there it is. I hadn't realized I was just doing the thing this way. But that means that you can, for a given X, you can shoot up all the Legendre polynomials, n equals, well, here we've done 2, you can again do 3 in this way and so forth. And the actual computer programs that compute the Legendre polynomials for arbitrary n and x probably use this. They don't use Rodriguez's formula, and they don't do what we were doing in the very beginning of using the two conditions and figuring out what all the coefficients are. They use this recurrence relation. So that in fact is one of the utilities of recurrence relations, is that you can use them to find all the values of a given special function. There are various other recurrence relations for derivatives, and well, I think nonetheless the important recurrence relation is this one. And we have here the generating function, and we can use the generating function to find out things about Legendre polynomials, in particular g of t and -1. Well, let's remember what g is. And I, of course, forget what g is, so I have to go back to find g. All right, so g, by the way, g comes from something that occurs in physics. That's why we have it. In other words, g of t and x is equal to 1 over the square root of 1 minus 2xt plus t squared. And this actually comes from, and let me just say, this is then sum n equals 0 to infinity of t to the n, and that's Pn of x. I don't want to write it as just Pn of x. But I wanted to say where this comes from. Well, it comes from Poisson's equation. So let's look at this. You see the Green's function for the Laplacian, in other words, the thing that you have that you wind up staring at in an electrostatics class over and over again. You have 1 over 4 pi absolute value, or the distance between 2 points in 3 space, 1 over 4 pi distance between the 2 points. That's g of the difference of the 2 points. And so what is that difference? Well, it's, maybe I should put in the step that was skipped here. In other words, g of, let me just use r minus r prime. This is 1 over the distance, r minus r prime, where these are both 3 vectors. And so this is 1 over the square root of this thing squared. And so that squared is r squared minus 2r dot r prime plus r prime squared. And normally we call that cosine theta. And so this is 1 over square root of r squared minus 2r prime cos theta plus r prime squared. That's another way of writing it. And if we then go to some limit in which r prime is small and r is big, then we would say g of r minus little r is equal to 1 over square root of big R squared minus 2 r little r cos theta plus little r squared. And then what you do is you factor out big R squared, and so you get 1 over r times 1 over square root of 1 minus 2 r over big R plus r over big R squared. And now what we see is that this is equal to 1 over big R times little g of t and x, where t is little r over big R and x is equal to cosine of theta. One often abbreviates x as cosine of theta. So basically, you start with this thing that's that comes out of electrostatics. In other words, Gauss's law tells you that the static potential is an integral 1 over 4 pi times, I think, the electric constant. And then you integrate over the charge density and you divide by the distance. And so you have this structure all the time. In other words, you have something like this: phi of x is equal to, I think I'm getting the signs and the pi's right, integral rho of y d cubed y over x minus y, absolute value of x minus y. And so it's this 1 over, this is this, well, I switched from r and r prime to x and y. Anyway, if we go back to r and r prime, what we have is this structure, and then you get this and this. And now if you let r be big and r prime be small, you have this structure here, and that gives you the generating function again. So that's why this is so important. And the curious thing about the generating function is that it is the Green's function. And it then occurs to me to ask, is it more generally, is it true for other systems of polynomials or of special functions that the generating function is closely related to the Green's function of the physical problem that gave rise to the differential equation in the first place. I don't know the answer to that. I encourage the students to Google that and figure it out. It would be quite interesting if it were generally true. So what, so anyways, I said we were going to get the special values of these Legendre polynomials. And so what you do is you say g of t minus 1. Well, what is g? Well, g, you see, is g is 1 minus 2xt plus t squared. And so if you have g of t and minus 1, you have a 2t and a t squared. And of course, that's just 1 plus t squared. And then that's a sum minus t to the n. And then because it's a generating function, it has to be t to the n times pn of minus 1. And so you find that pn of minus 1 is just minus 1 to the n. So you see these generating functions are really lovely things. They just give you so much information. If instead we say, well, what is pn of 1? Well, just to check this out, what we'd have would be g of t and 1 would be 1 over 1 minus t. This would be the sum t to the n, and this would have to be sum pn of 1 t to the n, and so pn of 1 is just equal to 1. So that's how that works. And you can then figure out, well, what's pn of what if you said x equal to 0? Well, then you would have g of t and 0 is 1 over, let me go back to the definition of g. I keep forgetting what the definition of g is. It's 1 over the square root of, oh my God, undo. Square root of 1 plus t squared. So there's nothing particularly simple about that. But what we can see from that is that this is obviously sum of P2n time P2n of 0 times t to the 2n. That is to say, you can't have any odd terms in t occur because this thing only involves t squared. And that tells us then that P2n plus 1 of 0 is equal to 0. And that, in fact, is what one gets here, namely that P2n plus 1 of 0 is 0. And on the other hand, P2n of 0 is something involving double ratio of double factorials. So that's a bit complicated. I'm going to, let me just tell you, I've added a new problem, not to the homework, the current homework, but to the homework due, I don't know, the 8th of November or something, somewhere in November. I've added a problem that's not in the book because I wanted to give you something, give you the opportunity to do an example like the example that I did in the first 15 or 20 minutes of today's class. So, and I think it's important for you to struggle through one of them and keep track of all the things. And this example is at, let me show it to you. It's oh Christ, I'm in the wrong chapter. All right, hold on here. Right. Okay. Find the integral equation for this ordinary differential equation, u double prime plus xu prime plus x squared u equals cosh. So it's very much like the one I did in class. It's just that I interchanged x and x squared, and I replaced cosh by sine by cosh. So I kept the interval, though, so that you won't have to keep track of u of a. U of a is going to be 0, and so the equations will be simpler. All right, well, we're over time. Let me just remind you that I've changed the office hours. Nobody came again. But since I'm doing them via Zoom, it's not that big a deal for me. If nobody comes, well, nobody comes. But now, since nobody came between 3 and 5, I'm changing the hours to 4 to 6. But again, it's on the class website. Now, somebody just told me here that 8.3 is written on the class website. Oh. So that's interesting. And that was a problem. All right, now I'm completely confused. Do you mean it was assigned, or do you mean that that the solution appears? Oh, okay, thank you. That's yes, I knew that. I'm not talking about 8.3. I'm talking about 8.4, and 8.4 will be for the homework after this one. 8.3 is for the coming homework. 8.4 will be a later homework. And about what is this? Well, anyway. So that's the way it is. I just think you need more exercise, and I guess in 8.3 you sort of can follow the example. In 8.4 you can follow what I did in class today. But it's good I think, for you guys to do it twice. All right, I'm going to say goodbye. I'm going to stop. I'll put it on the on YouTube tonight and send you the link. Bye, everybody. And thanks for